Looks like we're live. Hello everyone and welcome to yet another Azozin session. So let's make a little bit of announcement on our Discord server and officially start the stream. So red circle live on Twitch. What are we doing today on Twitch? Today we are rendering 3D model with Olivettes. Or Olivc, that depends on how you pronounce it. I'm gonna give the link to the Twitch chat where all of that is happening, and I'm gonna ping everyone who's interested in being pinged. And there you go, the stream has been officially started. So, Olivc is a simple software rendering library that we've been developing for quite some time. You can find it in here if you're interested. So I'm gonna copy paste the link in the chat, and also I'm gonna put it in the description for people who watch on YouTube. So it doesn't really have any third-party dependencies. It renders everything into the memory, right? In fact, it's just a sophisticated mem set or mem copy, right? So you just allocate a chunk of memory, and then you give that chunk of memory to the library, and you tell the library what to render there, and it just renders that into the memory. You take the memory, and it's up to you what to do with that memory. You can put it on a screen, you can save it into a file. It's none of the concern of the library. So that's basically the general idea of the library, right? So, and we started to go into realm of 3D for some reason. You know how the scope usually of the project grows and grows, and we now are doing 3D. So on the previous stream we developed 3D texturing, right? So essentially we have a 3D object, and we are now capable of slapping a texture onto that 3D object. So let's actually take a look at how it looks like. So we already have a demo compiled, right? So here's the website where we took all of the demos from the library, we compiled them to WebAssembly, and we put them in a single page. And there's a lot of examples in here, that's why it's lagging, right? So this is a bunch of 3D stuff, resizing, and this is what we started to do recently. We went into the realm of things that looks like OpenGL, right? So this is definitely looks like OpenGL, but it's not using OpenGL. That's what's interesting. It's completely on CPU, right? And the fact that it has the reasonable speed is because we only have 2 triangles. I'm pretty sure if we add more, it's gonna have like 1 FPS or maybe like -1 FPS, I don't know. So rotating texture, and this is what we developed yesterday. We now learned how to take the texture and put it into 3-dimensional triangle. So, and here's an interesting stuff. We already know how to do 3D triangles and stuff like that, and I thought, we can just try to go ahead and render maybe something more sophisticated. For example, a 3D model. You know, maybe just a single frame. It doesn't have to be animated, right? Because the 3D model is probably going to have a lot of triangles, and our software renderer is going to actually drown in all of these triangles. But we can just, you know, see if it looks like something. For example, we can take the Utah Teapot. Are you guys familiar with the Utah Teapot? It's just like a 3D model that is used for testing 3D rendering and stuff like that. It's quite famous Teapot. Right, and for instance, we can just find Utah Teapot OBJ file download. Right, just find OBJ file. There is an OBJ file from from the Standard University, right? So, and yeah, here are all of the vertices of this Teapot, and here are all of the faces. And the OBJ format is actually rather simple. We can just go ahead and parse it, and then, and since we know all of the triangles, we can just like render that. Sounds good? Sounds good? Sounds too good? So, and that's what I want you to do today. I'm gonna put the link to the Utah Teapot that we're gonna use today in the description as well, if anyone is interested. So maybe in the chat, I'm gonna post it here as well, right? So, and let's go ahead and do that. But before I go ahead and do that, I would like to finish that thing with generalizing the Triangle API, because we're going into the realm of things that require a lot of flexibility in how we interpolate values of the values that are associated with the vertices of the triangles. And right now we have a little bit of a mess with the API, with the Triangle API specifically. Right, so triangle. So we have 4 different functions for rendering triangles. The first one renders just a solid color. Another one renders the triangle with 3 colors, color per vertex, right? So it actually interpolates them and stuff like that. So a thing that renders a triangle in 3D space, and it actually treats the canvas as the Z buffer, and it actually stores the float in U32 because it's a hack, because we program in C and we don't have generics and stuff like that. And it's like it's a function for a very specific case, for our specific case. And we have another function for texturing, which accepts not only Z coordinates, but also a texture and UV coordinates, right? And what's interesting is that all of these 4 functions, they are basically a copy-paste of each other, with the body, with the small body that does actual work, replaced with something else depending on what we want to do. So there is a lot of like code duplicate between these 4 functions, and I already said it on the previous stream. We need to do something about that. We need to come up with a generalized triangle rendering mechanism that we can use, that can actually take into account all of these cases and maybe even more. You know what I mean? Right, and furthermore, I don't want the library to be aware of such things as Z, UV, and some other stuff, right? So I want it to be more or less general. I think I come up with the way to go forward. Okay, so Fortran Live, thank you so much for tier 1 subscription. Thank you. All right. So let me actually show you what I mean. So essentially what I want to have. So let's create something like try.c. So this is going to be an example where we test the API update, right? So this is going to be something like that. And let me also include olive C. And I'm going to also define olive C implementation. And let's go. So this is going to be hello world. You know what? I think I'm going to build this program with my build script. I'm just going to disable building the assets test and stuff like that. I'm going to say, okay, build try.c, and we also have a common flag. So this is probably the reason why I want to use this script, because I have a variable common flags, which contains a lot of useful flags that I want to use anyway, like these ones. All right, so, and let's go ahead and just like try to build that, and as you can see, it built try, and there we go. So, as it usually is with Olive C application, right, you're supposed to allocate your own memory. The library is not concerned with memory allocation, it's only concerned with filling the memory with whatever you give it. Right, so we're going to define the size of the canvas. Let's say it's going to be 800 by 600, right? So this is going to be the height, 600. And let's literally allocate the canvas, the like pixel array of pixels in the static memory, right? Because this is the easiest kind of memory to manage, right? You literally don't have to manage, right? It's just allocated automatically. It lives for the entirety of the program, and then it's deallocated automatically, right? You literally don't have to do anything. All right, so we're going to turn these pixels into Olive C canvas, and Olive C canvas is basically a lightweight view on an array of pixels, right? It doesn't really own pixels, it's only referring to them. It's like a string view, but for pixels, right? So it's a pixel view. So Olive C canvas, it is going to accept the pixels. Canvas accept the pixels, width and height, and also the stride. And in our case, the stride is going to be equal to width. Right, and let's go ahead and maybe fill this entire thing with some sort of a background color. Let's say that the background color is going to be something like red, right? So just we can see what is going on here. Right, so let me try to build this entire thing. Right, it's building. Cool. So, and after that, I probably want to save this entire thing into the file, just to see like what's going on in there. So we're going to be probably using stb library, stb image write, this one, right, because it can actually generate png images. So let's include stb image write.h, and we also have to include implementation macro, right, like so. And let me find stb image. I think it's called stbi write, right, there you go. So after we generated a thing, we want to do what? File path, width, height. The amount of components per pixel is going to be 4, right? We have 32-bit pixels. The data is the pixels themselves, and the stride is basically the width, but in bytes, not in pixels. So size of a single pixel is int32t, and we're going to multiply it by width. So, and this entire thing returns true if it succeeded and false if it failed, right? So, and if it failed, we're going to literally just say std error, could not write file. We're going to specify the file that we couldn't write, and then we're going to exit with non-zero exit code, and that should be fine. Right, so probably also want to specify the file path, right? So this is going to be file path, and the file path is going to be try png, right? So there we go. So I think we set up the workbench where we can test the update of the API. So let me try to build this entire thing, and it's buildable, and let's go in here. So here is the try executable, and if I try to execute it, executable, it generated try png, and it's filled with red color as we expected. So let's actually replace the red color with a neutral color, like a gray color, right? So, and I'm gonna build and run this entire thing simultaneously. Right, there you go. And then if we take a look, so basically it's the same background as the background of the text editor, right? Which is kind of nice. All right, so what kind of API I want to have instead of whatever we have right now, right? Something more generic. So essentially, I want it to be sort of lazy, right? You start rendering a triangle by saying something like triangle, and you say Olivet's triangle new, right, for instance. And this is where you would specify the vertices of triangle x1, y1, x2, y2, x3, y3, right. And basically this entire object encapsulates the state of the algorithm that renders the triangle, right. So that's what I want to have. So then you would basically ask it, what are the vertical boundaries of the triangle, right? Because we're rendering triangle from top to bottom, from left to right. So we're scanning it, and then we render the lines that, like horizontal lines that form the triangle. So that means we need to know the sort of vertical boundaries. For that, we can introduce some sort of a function of C triangle vertical bound, right? So, and in here, I would expect it to accept the triangle that we just created, right? And also, we are going to pass a couple of variables that will form a boundary. But here's an interesting thing. If the triangle is completely out of screen, right, so we shouldn't render anything. Right, we shouldn't render anything. So I suppose this function should also return true or false, depending on whether you have something on the screen to render or not. Right, for example, if this entire thing does have a vertical boundary, that means we need to go ahead and just render it. And we're going to render it from top to bottom, right? So we're going to do for y, y1, y2 plus plus y, right? So it's, I suppose it's going to be similar to how like a normalized rectangle works. Normalized rectangle. So essentially, the function accepts a rectangle and a canvas, right, or the size of the canvas. And essentially, it basically normalizes the rectangle and gives you the ranges, like vertical and horizontal ranges, that are safe to iterate and access without doing any buffer overflows or anything like that, right? So, and if the rectangle that you provided is outside of the canvas, this function returns false, and you put it into the if, and so you never actually iterate anything if there's nothing to draw. So I want this, like a vertical bound for the triangle, to be kind of a similar situation, right? So you basically request what is the vertical boundary for the triangle. Okay, here it is, but if it's outside of the scope, outside of the canvas, it returns false, so you don't have to render anything. So something like that. All right. So here's another interesting thing. So you know the vertical boundaries, but now you need to know horizontal boundaries. And the horizontal boundaries depend on y, because they are different, because this is a triangle, it has a variable sort of width and stuff like that. Right, so, and essentially you're going to have a second similar function that we can call something like horizontal bound, right? Triangle horizontal bound. So here you provide the triangle, So since the boundary, the horizontal boundary is going to be different depending on the y, we have to supply the current to y, and we have to supply the pointer to x1 and x2, right? And of course, this entire thing might be outside of the screen completely, so we can check for that, and if it's true, only then we can go ahead and start iterating from x1 less or equal x2 plus x. And there you go. So inside of this loop we have x and y, and what we're effectively doing, we're iterating through each individual pixel of the triangle with vertices x1, y1, x2, y2, x3, y3. Right, so this is like nested loop that iterates through each individual pixel of that specific triangle. And what you can effectively do, right, Olivet's pixel, you can take that pixel of that canvas, and for example, you can put some sort of a color in there, right? So let's say it's going to be sort of like reddish. So, but you can go even further. If you want to do the triangle interpolation, the if you want to take the barycentric coordinates, if you want to like have a gradient, we're going to have another function, right? Olivet's triangle barycentric, right? So you're going to provide the triangle itself and the x and y coordinates of the current point, right? So, and then you probably want to allocate the variables that will hold the barycentric coordinates, right? The determinant, and then you provide the pointers to those things, right? And there you go, you have barycentric coordinates, so you can use them, for example, to mix the colors, right? And get that rainbowish triangle. So mix colors like so. So it's going to be try. So let me you int 32. Boom, boom. There we go. So here we're gonna have ff18 ff. So ff18 ff18 18. Right, so in here we have the values of the barycentric coordinates. So this one's going to be u1, u2, determinant minus u1 minus u2, and the determinant itself, right, something like that. And so since you can take the barycentric coordinates, you can also do the interpolation of the z values or uv coordinates. And what's funny is that you don't need the OLIVC library itself to be even aware of such things as z interpolation or 1 over z interpolation or UV coordinate interpolation, because the only thing that OLIVC will provide once we implement this entire interface is basically iterating through the pixels of the triangle and getting the barycentric coordinates of that specific pixel. And that is more general mechanism that is more convenient and will help us to get rid of this duplicate code. So essentially what we're going to have like a 4 functions, I suppose. So triangle new, the thing that creates a new triangle. Vertical bound, horizontal bound, and barycentric coordinates, right? So we need these things. Maybe they're too long, so I could have actually called them maybe try. Olivet's try new, vertical, bound, horizontal. Maybe because of that I can actually get rid of the bound, so it's a try new, vertical, horizontal, and barycentric. Yeah, isn't that cool? Isn't that cool? It's pretty fucking cool. So there's no like one extra character to actually align them perfectly. Okay, doesn't really matter. So this is the triangle, but we have to prefix everything with OLIVC, so I think I'm gonna call it OLIVC like try triangle. Or since I'm not planning to use it very often, I might as well just call it a triangle. Whatever. So Olivet's triangle. Olivet's triangle. So I would like to also have as a reference the function that actually draws the triangle. So triangle 3C, I think triangle 3C is a good candidate for copy pasting in here. Right, so here is the algorithm, right? So here's the entire algorithm, and I'm probably going to actually comment it out so it doesn't get compiled. So what do we need to have inside of the triangle? First of all, we need to store all of these coordinates, right? So let's actually go ahead and do that. Let's grab those coordinates and let's put them into the structure. So we want to have those things. Right, we want to have those things. So here it is. So another interesting thing, we could probably put these things into the triangle as well, but they're basically pre-calculations, right? So we can calculate them, yeah, we can calculate them every time we're about to take the boundaries, the vertical or horizontal boundaries, so I think I'm not going to store that. So the most important thing in here is we always sort the vertices, right? Because we expect them to be in a specific vertical order, right? Because we are rendering from top to bottom. So when we change the order of the vertices, the data associated with those vertices can change as well. And that will affect what barycentric coordinates actually mean. So, and this is kind of like a very inconvenient problem that I was thinking to implement the following way. I was thinking that I'm going to actually store the order of the vertices, and as I sort those vertices, I'm going to actually keep the original order. So when I'm about to take the barycentric coordinates, I reverse back them into the original order, right, and I just take barycentric coordinates of the original order of the vertices, right. And since it's stored in the array, right, because we want this thing to be based on index, storing these vertices like that is not particularly convenient. You want to have something like points 3, or this require I will create in a structure so I can actually have parallel arrays. So here I'm going to have x's and here I'm going to have y's, right? So I have an array of x's, I have an array of y's, and I have an array that stores the original order of these points of the triangle, right? So that's essentially the data structure. So maybe we're going to extend the data structure, maybe we're going to add something else in here, but for now the only thing I need is the points of the triangle and their original order. So all of that is supposed to be encapsulated by the structure, so the user of the structure should not know what's inside of it, or maybe we'll see. So if you want to know what's inside of the structure, well, feel free to know. Who am I to tell you what to do? Okay, so here I'm going to accept yes, int x1. So, but the arguments are going to be original like that, right? x1, y1, x2, y2, x3, y3, because the rest of the code kind of expects these specific arguments. All right, let's create the triangle, right, that we're going to return after we initialized everything. Right, and the first thing I want to initialize is the order, right? So the order is going to be 0, 1, 2. That's the original order. And then we're going to change that order as we're going to change the values of x's and y's, right? So x's are x1, x2, x3, right? So this is x's, and then we're going to have y's. There we go. So we already initialized everything, but this is not enough. We need to sort them. So since we need to sort only 3 points, we don't use any sophisticated, sorting algorithm, right? So we literally just hard code 3 iterations of a bubble sort, right? So it's actually kind of funny. People say that bubble sort is so slow because it's a square, it's a O of square sorting algorithm, that's why you should never use it. Well, it's actually not entirely true. It's true in most of the cases. I do agree with that. In most of the cases, you don't want to use bubble sort, but saying that bubble sort is always slower than any of the n log n sorts is actually not entirely correct. Yeah, so what's interesting is that for small n, n squared sorting algorithms might be faster than n log n sorting algorithms, right? Because n log n actually speed up because of some additional constant cost, right? And square algorithm may not have that additional constant cost, and because of that, on smaller data, that could be actually faster. This is O of 1. No, if n is the amount of vertices, this is O like n squared. It depends on what you consider a constant. It depends on the definition. Now, what we're gonna have. So let's actually start doing this kind of thing. So we're gonna compare. I'm thinking, can I actually do something super smart? I'm gonna query replace. So first of all, I don't care about the colors, right? I don't care about the colors. So I'm gonna query replace by regular expression. So I'm gonna have x and y, right? So here's the x and y. And then I'm going to have 1, 2, 3, right? 1, 2, 3. So these are two things. So, and what I'm going to be replacing them with, I'm going to replace them with try dot 1, and since there's many of them, it's going to be s, and then 2. There we go. So yeah, there we go. So this is basically what I want to do. So the problem here is that they start indexing from 1, and we have array that index things from 0. So, but it's actually rather easy to fix, so I don't really care about it right now. And most importantly, we have to keep the order along with those things, right? So this is going to be the order. And here we have another order, and we have another order in here. All right, there we go, there we go. So this is how we maintain the original order, right? So, and another thing is that I'm gonna query replace 1 with 0, right? Because we have a 0-based indexing. Then we're gonna replace 2 with 1, there we go, and 3 with 2. 3 with 2. There we go. All right, so this is basically the sorting, and I don't think we need anything else. I think this is totally fine, right? I think this is totally fine. All right, so what do we have in here? Oh, okay, so we have this code that is like doesn't really work yet. So I'm going to simply just, you know, comment it out. So I'm going to simply comment it out. Cool. Now, might as well not completely comment it out, so I can actually put this thing in here and just like maybe look what's inside of this entire thing. Oh, yeah, so what kind of triangle do we want to render actually? So let me think. I want to put like a regular, you know, equilateral triangle at the center of the screen. I think that will make sense. Right, so let's actually start the point at the left, and the width, the x is going to be third of the width, right? So this is going to be third of the width. So height is going to be actually 2/3 of the width, right? 2/3 of the width, so it's going to be like down there. So another one is going to be at the center, and then third of the height, right? Somewhere there. And the last one is going to be actually 2/3 of the width and 2/3 of the heights. There we go. So we're going to have something like this. So this is the triangle that we effectively created. Okay, so, and oh yeah, so I actually renamed this entire thing. Oh, yeah, it's called new. Okay, cool. So I would like to actually take a look at what we have in there. All right. 7 Olive C, GDB, and we're going to try. So, and I'm going to break at main and run and TUI enable. Right, so let's actually go through this entire thing. And let me just print the structure, and let's take a look at the structure. So this is basically what we have in here. And it got sorted. Some of the values got swapped, and here's the, like, here how we store the original order of those things. So this is quite important. Right, so everything seems to be working, at least in the debugger. We'll see how it goes further. So now we need to implement something like vertical bound, right? So I actually renamed this entire thing, but bound. So try, I just called it try vert, right? And another one is going to be try horizontal. And the last one is going to be try barycentric. Yeah, try barycentric. All right. So in here, we're going to return boolean. We accept the Olivet's let's try. And do we need to accept anything else? Right, so we need to accept the boundaries themselves, right? It's going to be y1, y2, and here we're going to return something like false. And this entire thing is also going to probably accept, it also needs to accept height. I just realized that, because it somehow needs to know if the triangle that you're trying to render is out of bounds, and we only check the vertical bounds within this this particular function, so it makes sense to also pass the height of the canvas, right? And what we're going to do in here, well, so the first half of a triangle goes from y1 to y2, and the second one goes from y2 to y3. That means that the vertical boundaries of the triangle are y1 and y3. We know that y1 is going to be the highest point, or the smallest in terms of y, because y goes down, and the third one is going to be the lowest one, right, or the biggest. So we essentially can return those, right? So we essentially can return those, and it's going to be y1 is try, y is 0, and y2 is going to be y is 2. There we go. So, but here's an interesting thing. They can actually overflow. What if y1 is going to be less than 0? So that means you can't start iterating from it, because you will try to touch the memory that you're not supposed to touch. So we can do something like this. If y1 is less than 0, we can say y1 is going to be equal to 0. That's it, right? So we sort of clamp it. Right, it's sort of a way to clamp this thing. So we also can have another situation when y1 is greater or equal than height. It also means that it's bigger, but this one is actually rather interesting. We know for a fact, always, I can even put it somewhere here. So there's a very interesting fact, which I'm probably going to remove, because, I mean, we'll have to do that on each line, which might be expensive. We know for a fact that y1 is less than equal to y2. Which means that if y1 is greater than height, that means y2 is also greater or equal than height. So that means the entire triangle is invisible. It's entirely out of bounds, down there somewhere. Which means that in this case we can just always return false. Right? There's no even point to continue trying to figure out the boundaries, like, yeah, so just bail out. Let's do the same thing for this for the second one, right? So if y2 is less than 0, it's kind of a similar situation to this one, but symmetrical. If y1 is less than 0, that means y1 is also less than 0. So that means in this case it's false. But if y2 is greater or equal than height, in that case we can clamp it. We can set it height -1. So, which is rather interesting. So we can see that these two cases are kind of symmetrical, right? They are kind of symmetrical, and if we pass through the entire thing, we can quite safely say that you can actually render that triangle, right? So there you go. This is basically what we have in here. So maybe we can try to, I don't know, render something. So we can disable this specific piece of code, right? So we're not going to render anything, and in here we can basically render a single line, Olivet's line. So let me actually find the Olivet's line. Olivet's line. All right. So this one is going to be that. So this is the canvas. In terms of x, it will probably start from 0. So I'm going to just like draw the lines for each row of the triangle, but from the left side to the right side. So it's not going to be triangle, but it's going to be a rectangle with the height of the triangle. So y is going to be the current y. X is going to be the right x, but it has to be -1, right? So, and this one is going to be y, and the color that we're going to put in there is going to be FF 8080 FF. There we go. So this is what we want to have. So less or equal than height. So, oh yeah. So height is unsigned, and this one is signed. But we know that it's greater or equal than 0, so that means it's safe to cast it to unsigned one. Similar situation is in here. Right, we know that it's going to be non-negative, so we can just do it like that. So this one is supposed to be a pointer, and we don't have such functions in here, so we probably have to allocate them on the stack. What else do we need in here? Nothing, actually. Or, oh yeah, I have to provide the height. So let's provide the height. Okay, cool. So let's take a look at the try PNG, and there we go. So maybe I would actually make the background a little bit brighter, so we can see the boundaries of the image itself, because right now it's not particularly clear where the boundaries of the image and what is the actual text editor. You know what I mean? It's kind of not particularly clear. Okay, so here's the image, and this is the height of the triangle. We don't know what the horizontal boundaries are, but we know the vertical boundaries. So essentially what we need to do, we need to now carve a triangle out of this entire thing. All right, so and this is what we're gonna do in try horse, I suppose. We're gonna try the horse. All right, we're gonna try the horse, and so here we're gonna be accepting Olivet's try. So this is going to be y, and we probably have to also accept the width in here, right? So we have to accept the width, right? And it's going to be x1, it's going to be pointer, and it's going to be x2. All right. False. Cool. So how we're going to be doing that, and this is rather interesting, right? So the actual boundaries, the actual horizontal boundaries of the triangle are going to depend on y, and in which part of the triangle are we? Are we in the upper part of the triangle or the bottom part of the triangle, right? So in the original code, we even had two separate for loops for two parts of the triangle. Right, so, but now we have to sort of put this entire logic inside out. So, when are we in upper part of the triangle? We are in upper part of the triangle when y is greater than y1 and less than y2. Right, that means we are in the upper triangle. Otherwise, if we are between y2 and y3, we are in the bottom triangle. Otherwise, we're probably somewhere outside of the boundaries, right? Which shouldn't happen if you follow try-vert, but you cannot guarantee that the core of horse actually followed this thing. You cannot guarantee that, so we probably want to check that. So that means we're out of bounds. And if we are in out of bounds, it makes sense to instantly return false. Like, there is literally no reason to try to render anything in here. Just indicate to the user that, you know, you did a oopsie doopsie and potentially fucky wacky. Okay, so, but we don't have like y1, y2 and stuff like that. So maybe I'm gonna actually do the following thing. So x1 is gonna be, so this is gonna be a pointer try, access 0. And I wonder if I can just do something like this. 3, 1, 2, right. And I'm going to query replace x with y. There we go. So, and the reason why I want to have this as a variable is because it will allow me to copy paste the code from the previous implementation, because the previous implementation referred to those things as x1, x2, and x3. Right, and new implementation uses the indices, so, but it makes it difficult to adapt the code. And the indices I needed to restore the original order of the vertices, right? So it's quite important in my opinion. So yeah, basically need to re-implement this entire logic, right? So this is where we figure out the boundaries. So S1 and S2 are basically X1 and X2 in this particular algorithm. I didn't really know why I called them S1 and S2. But it was a long time ago, so maybe I was drunk, even though I don't drink alcohol at all. So this is the first logic, right? So we don't really need any of this stuff. But yeah. So what effectively we have in here, we have X1 and X2, right? And then we also swap them. In fact, we're gonna do the same thing in the bottom triangle, so maybe it makes sense to actually put this entire thing in here, right? So if, for instance, x1, x2, right, that means we need to swap them, right? Because I want to keep x1 and x2 in a order, right? So I think it's quite important, but I don't remember if it's actually needed. Maybe it's not even needed in here, but I know I decided to put it here anyway. So this is the upper triangle. We need to do the same thing for the lower triangle. So this is going to be the lower triangle. So this is not needed. Then I can probably replace this entire stuff with x. There we go. So these are the boundaries, and if x1 turns out to be bigger, we actually want to swap them because we expect x1 to be always smaller. But here's an interesting thing. Like we have a similar situation as with the vertical boundaries. What if some of them are out of bounds, right? So we need to do a similar thing. So essentially, if x1 is less than 0, that means we need to make it equal to 0, right? If x1 is greater or equal than width, and we know we already even like ensured that x1 is always less or equal than x2. That means this entire thing is outside of the scope, outside of the boundaries, not the scope. So we can like instantly return false. And we need to repeat the same thing for x2, but in a sort of symmetrical way. For x2, if it's less than 0, that means we instantly return false. But if x2 is greater or equal than width, that means it has to be x2 equal width minus 1, right? Something like that. And if we went through all of these checks, that means we found that one horizontal line that we need to actually render, so we can actually return true, right? So there you go. This is what we can do in here. So let me see if it compiles, right? It doesn't really compile because we have a redefinition. Oh boy, oh boy, oh boy. So maybe I should call it S1. Right. Okay. I think I'm starting to understand why I decided to call them S1 and S2 instead of X1, X2. Yeah. I kind of literally rediscovered that. Okay, we replace x1 s1, and we're gonna have another one x2 s2. There we go. Cool. And so we have a width situation, which is like the same. All right, so this is gonna be size t, and there we go. Boom. Okay. So show me triangle. Show me a triangle. And it didn't work because I didn't use the functionality that I just implemented. Okay, so what we have to do, essentially, all right, so let's not render anything, right? So here's the vertical, we're iterating each individual row of the triangle, and for each row, we're figuring out the boundaries of that row, and the only thing we need to do, we need to just iterate through those boundaries and set their pixels to some color, right? So it's going to be FF, 80, 80, FF, and there you go. That should be enough, right? I'm going to even remove that. So this is how you can fill the triangle, right? You organize the triangle, then you basically iterate in it in two-dimensional loop like it's a rectangle, but these two functions kind of help you to find the boundaries so you're not iterating the rectangle. Right, so let me see. So what we have in here, we have to probably provide the width as well, right? We have to provide the width as well. So x1, yeah, we need to also provide x1, x2. There we go. And let's go. So let's actually open PNG. Dab, it's a triangle. And here's the cool thing. If we want to have a rainbow triangle, right? So we only need to add another function for the you know, triangle interpolation, right? For the triangle interpolation, and as soon as we implement that, we'll be able to actually do like a rainbowish triangle, right? So let's actually put it like this. So I don't think it needs to return anything, right? So let me take a look at what it's supposed to accept. Right, definitely it is going to accept Olivet's try. So this is going to be a triangle. And it's going to accept the current point, right? It's going to accept the current point and also the output for the barycentric coordinates, right? So it's going to be u1, a pointer, then u2, and then the determinant, right? There we go. So we already have the function, right? So we already have the function for barycentric coordinates. Where's the barycentric? There you go. Okay. We could just use that, right? We could just use that. But it's kind of dangerous. So here's the thing. We put vertices in this specific order into the triangle, but the try new may reorder them however it wants. So that means you cannot just use this function and provide the same vertices because you're going to be referring to the wrong vertices, right? You're going to be referring to the wrong vertices. Or maybe you can. Can you? Well, yeah, you can, but you have to store the original vertices. You need to store the original vertices. But we already kind of store them inside of this thing, yeah. So essentially what we'll have to do, right? So let's actually recreate this thing back, right? Let's recreate this thing back. And we need them in the original order as the user provided. So for that, we have the secondary array of indices. Try order, boom. And because of that, it is now in the original order. Isn't it cool? I think it's pretty freaking cool. My God. Okay, so now we just put this thing in here. Then the original point, the point that the user provided, x, y, and the pointers. There we go. Yep, so that's basically it. So that's entirely the reason why we store this original order array, so we can actually recreate it when we take the bare standard coordinates. And bare standard coordinates are really important because they allow you to interpolate, for example, colors or anything you want. So let's actually go ahead and interpolate the colors. So I'm going to grab this function. I'm going to grab this function and provide the triangle. Right, so here's the triangle, here is the point to which we want to interpolate. Then here are the bare standard coordinates, u1, u2, and determinant. Right. So, and we have a function already, Olivet mix colors 3. So it allows you to mix 3 different colors, right? So the first color is gonna be red, I suppose. FF 80 80 FF. The next one is gonna be green, right? And the next one is going to be blue, right? And the way it's going to work, we provide the first bare standard coordinates, the second one, the third one can be computed from the determinant, u1 and u2, and then we provide the determinant itself. So that will mix these 3 colors in a correct proportion, forming the rainbow triangle. Hopefully, we'll see how it goes. So Olivet's pixel, and what you don't like? Okay, I forgot semicolon here. Cool. So let me take a look at the PNG, and there you go. So we've got the rainbow triangle. Cool. So as you can see, you have the bare standard coordinates exposed now, right? So they are not computed inside of the API, not in the implementation. They are now outside. The user of the function now always knows the bare standard coordinates of the current point, which means that these 4 functions is the only thing you need to implement examples like this. So triangle, what was that, demo, triangle 3D texture SDL, right? So yeah, so these are the only 4 functions that you need, because here we do a lot of interesting things. I think we do 3 different interpolations in here. 3 different interpolations. The first one is the color interpolation of that one triangle. So this is the color interpolation. Then we do interpolation of the 1/z values to do the proper shading and the z buffering. And another interpolation that we do UV coordinates interpolation for the texture triangle, and to cross them and stuff like that. So there's at least 3 different interpolations going on. 3 different interpolations going on right now, and for all of 3 of them I have 3 chunks of code that are literally copy-pasted because I didn't know how to generalize them, right? I didn't know how to generalize them. So now we have API that literally generalizes them, right? So you can use the same API to merge all of these 3 functions together. Maybe we should even try to do that, right? So essentially in a single loop I can just do all of the interpolations needed, and maybe even check the Z buffer. Yeah, so now the library itself shouldn't be even aware of such things as Z values and UV coordinates, right? So it just provides you this thing, and that's it. So that's actually kind of cool. All right, so isn't that cool? So we need to make this entire thing part of the library and just basically replace all of those functions. You know what would be cool? You know what would be cool? It would be cool to copy paste these implementations into the library. Do not delete any of these functions and simply implement those functions with the new API. So we can like keep them for backward compatibility with existing demos, but re-implement them with new, more general API and see if it works or not. So I think that's pretty cool. So that's exactly what we're gonna do. God, it took me 1 hour to do this. I thought it's gonna be quicker. It took me 1 hour to come up with a better API. Will we have enough time to actually do all that? Maybe we will. We'll see. Right. Thank you so much, Audacious Ferris, for Twitch Prime subscription. Thank you for Fortran Live for tier 1 subscription. Pog. So yeah, thank you. OBJ looks super easy. Yeah, it is. Well, I mean, the subset of OBJ that I plan to parse today is in fact extremely easy. So the only thing I want to parse today is this thing. And obviously, just to parse this, I'm not going to implement the full OBJ parser, right? So yeah. 1 hour would take me a lot more, lol. I mean, everything is relative. For example, if you have only 2 hours, 1 hour is half of a time, right? So now I have another hour to implement a parser and loader of this file, and then the renderer. Will I have time to do that? I don't know. So maybe I'm gonna skip the part where I implement the old legacy functions in a new API. I'm maybe gonna do that on screen because it's not that particularly interesting. And jump straight into parsing this OBJ. This is Utah Teapot, by the way, so the classical 3D thing. I'm gonna jump into parsing this file and then rendering it. So, oh, another cool thing is that all the vertices in here, so I presume these are the vertices, they are kind of close to the normalized coordinates. We'll probably will have to maybe scale them down, yeah, because I can only work with things. Yeah, I can only work with things that are normalized -1, -1, 1, and I think Z goes. Oh, in my case, Z goes from 1 to 2. Yeah, because of how I project things, it's easier for me to use Z from 1 to 2. But I can always just like, you know, squish and stretch and just like feed it there somehow. All right, so, okay. So let me go ahead and just copy paste this new API, brand new API to the library, so it's available for everyone for free. Imagine getting shit for free on the stream. Literally free code. Oh, and by the way, and since we don't really need to be aware of UV coordinates, we can remove all of that stuff from the library as well. So that's actually pretty cool. Really happy about that. So, all right. So I'm just like literally copy pasting those things. This is not what I wanted. Emacs only def. So this is the vertex. This is horizontal function. Here it is. And the last one is the barycentric thingy. Only that's def. So now let me grab all of that code. Let's try new vertical, horizontal, try bearing, and let's just like put it in here. Let's just put it in here. Okay, so also gonna remove that. Also going to remove that. Okay, so now all of that is part of the library, hopefully. Oh, this is not what I want. Okay, so did we call the try? I don't remember. I think I didn't. There we go. Cool. Implement a more general triangle rendering API. Something like that. I'm gonna push that right into the repo. Digital technology is a dead end. What about analog technology? Alright, so let's make a small break and you guys have fun. Alright, so let's go ahead and actually try to load this bad boy. So I'm gonna download this entire file. I wonder how heavy it is. So it's around 206 kilobytes, which is fine. Okay, so let me go ahead and maybe restructure this entire sort of file. Right. So I'm gonna just remove this entire thing and keep it like that. So we're gonna render that into this specific canvas, right? We're gonna render that into this specific canvas, but we also probably need to set up the projection. I'm gonna copy paste the projection from the existing examples, so no big deal. So first thing I want to do, I want to be able to load the entire file as a string. So I don't remember if I already have read entire file in here somewhere. So I never actually had that function anywhere, unfortunately. So I'll have to implement it. Is there any way for me to get it from somewhere? It looks like, oh man, I probably have to do that exercise yet again. Okay, I probably have to do that. So the only thing I need to do, read entire file. Let's quickly just do that. Okay, so file path. And we're gonna accept the pointer to the buffer into which you're gonna be saving all of that, and the pointer to the size of the buffer. I don't remember if I had this function already implemented anywhere, like nearby, where I can copy paste the implementation. But I thought I had it somewhere implemented in here. Yeah, okay, so let's actually just do that. So I'm gonna return error no. I'll probably need defer, return defer as well. Yeah, so this is, we don't have error no, but return defer, here it is. It's gonna be very useful. I'm gonna also define int as error no. There we go. So yeah, essentially, I like for my custom functions, I like to indicate error by returning error no rather than setting global variables, because setting global variables creates a lot of problems, an enormous amount of problems. Right. Okay. So, and I usually use this sort of like a defer pattern, which is kind of similar to how Go works. But yeah. So essentially you have a return defer function, which instead of returning actually goes to defer. So every time you refer from a function, it always executes some code in here. No matter from where you return, always before returning, it executes at least something. So this is kind of like a defer-like from Go. It's not really like defer, but I mean kind of close. It's just like you have to maintain this section manually yourself, right? So let's open a file, right? So this is going to be f open. We're going to open the file for reading in bytes, right? And if it failed, right, equal to null, I'm going to return defer error no. There we go. So something like that. It would be nice maybe to actually initialize this entire thing first with null, like so, and then the result is going to be initially 0. So, and in here, if f is not null, we're going to always close it, right? So it's going to always close this entire thing no matter what, right? So it's sort of like a defer thing, yeah. Okay, so next thing we have to do, we have to, you know, determine the size of the file. So we have to do fseek. Let me find fseek. Fseek, just jump there, please. Okay. So we provide the file, the offset is going to be 0, and we're going to set it to the end. And if this entire thing has failed, right, if this entire thing failed, we return error null. Okay, there we go. So the next thing we need to do, we need to figure out the size. We're going to take the current value of the cursor, and if it's less than 0, we yet again return the error null. There we go. So after that, we need to set this entire thing back to the beginning, right? We need to set it back to the beginning. So, interesting enough, now I need to allocate some memory, right? I need to allocate some memory, but that means I have to use malloc. I don't want to use malloc because that means I also have to manage it properly and stuff like that. I think I'm going to include an arena. I have an implementation. Yeah, I do have an implementation of arena in here, so we can do something like this. Arena implementation, and this is going to be arena. So if you never heard about arena allocator, arena allocator, I really recommend to check it out and read about it. Alright, so let me actually give it to you. There we go. And I'm gonna put that stuff in the description as well. So yeah, arena is basically like a region of memory where you can allocate memory as much as you want. And you don't even need to deallocate specific chunks of memory that you allocated. Yeah, you can just forget about them. And then Arena has a very interesting operation. You can say, okay, deallocate everything you allocated into that arena at once. So that's basically how it works. So usual malloc free is actually like you allocate a chunk of memory and then you have to deallocate that specific chunk of memory. You should not forget it. If you lose the pointer to that specific chunk of memory, you're fucked. You're fucking fucked. So in arena, it's actually slightly different. So you keep allocating into the same arena, and you can forget pointers to these chunks of memory. You can just like forget about them, and then at the end, you can say, okay, deallocate all these things at once. It's rather convenient because you can have a lot of small objects which have the same lifetime. And you don't have to keep track of their lifetimes, right? Because you know they have the same lifetime, so you can deallocate all of them at once. So it's rather convenient in my opinion. Well, it actually depends, right? So you may forget to maybe reset the arena at some point and you're gonna have memory leak. But for our cases, I think something like arena is actually rather convenient. So I actually use arena for testing, right? So I have a test, and for example, so every time a test is finished, it cleans up the entire arena. Then the next test comes in and the test actually loads an image, parses the image, then it generates the test case, compares, and all of that just wastes like memory. It just allocates the memory and never actually freezes that for the entirety of the test. And then when the test is finished, I just deallocate all of that mess at once, and then the next test already deallocates even more, and then I deallocate it, and so on and so forth. How the hell do you know the lifetime of your allocation? Because you write the code. You write the code so you know for how long you will need that object, right? So if you don't know for how long you need that language, do you even know what your program is doing? Like it's kind of a strange question. Like, are you aware of what your program is doing? So maybe you have a different problem. Maybe you need to investigate what your program is doing. Okay. So let me see. So I'm gonna just allocate some sort of a default arena. So maybe I'm gonna copy paste some stuff from the test C. So here is the default arena. So I also like to have this kind of thing, so I can switch the arenas if I need to. So let me put the stuff in here. And since we're gonna have an arena, I might actually as well allocate those pixels in the arena too. But we'll see. Okay, so and in here, by the way, we can do some cool stuff. For instance, we can say arena free, and this is going to be default arena, arena. Right. Defer like so. So it also requires a result, right? So let's actually set it like that. Okay. So arena implementation, not include but define. What else do we have in here? So we need to have error no, error no, and what else do we have? Okay, so we have this kind of stuff. Okay. So after that, I want to do context alloc, right? And it accepts the size of the allocation. The size is going to be basically m. Right, buffer size. Buffer size. Then I'm gonna read the entirety of the file into that specific buffer. So let me actually find the signature of a thread, so I can do this entire stuff. Okay, so this is gonna be buffer, the size of the buffer size, and it's going to be a single buffer that we want to read. Okay. So I don't really care what it returns because it doesn't matter. So what matters is the result of this thing. Return defer error no. Alright, so and after that we can, yeah, that is it actually, believe it or not, that is it. So after that the file is going to be automatically closed, and then we return the result, which is going to be 0. So this is how we read the entire file. So what we want to do in here, we want to read the entire file, right? So read entire file. The file is going to be what? OBJ is going to be Teapot. Might as well file path, right? Const char file path is equal to Teapot OBJ. Teapot OBJ. If error not equal to null, right? So as you can see, I'm already programming in Go, right? So error could not read file this, and might as well maybe print error no, why not? Str error, error no, and then return defer 1. There we go. So what we're gonna do, we can actually do something like printf, something like that. Printf z. We can say that this is going to be size of file, like so. And we know that the size of file, oh yeah, I didn't specify the buffer and the buffer size. So buffer and the buffer size. Buffer and the buffer size. There we go. So buffer and the buffer size. Okay, so I mean it's a big null. Sure. It's not even null, it's 0. Okay. Alright, so and string in here, so we have to provide the file path as well. So file path, it's already kind of like taken, so I suppose this is going to be input. So file path, obj file path, let's call it like this. So this is going to be obj file path. And this function realloc, we may actually use it in the future, but anyway, so let me try to run the try, and as you can see, so the size of the file is 210,614. Right, so and that's precisely the size. I mean, it's kind of like rounded up in a really weird way, but it's just like to be human readable, we can always do something like this Teapot, and we can clearly see that this thing matches that original number. So we actually read the entire file. The only thing we need to do with that file is to parse it, right? So we need to split it by lines and stuff like that, and so on and so forth. So to do that, I have a library that I also wrote myself, which is called SV. So we're going to be using SV to achieve that. I would watch Hots if I understood what the hell he's doing. He's developing TinyGrad as far as I can remember, right? So it's just like a gradient descent implementation in Python. Alright, so I'm gonna put this thing for machine learning in chat. This is not what I wanted. Why? Okay, that was dumb. Okay. I don't even know what I did. Where's the shell? It's still connecting. Okay, so it didn't even do anything. That's really, yeah. So it was actually doing some weird shit. Okay. Let's download the raw thing in here. I'm gonna do duplicate. Okay. So let's go ahead and try to parse this entire stuff. So I'm gonna be including this, I think. So sv.h, right, string view. Then sv implementation. All right, and string view sv. So let's actually call it maybe content, right? So let's call it content. Sv from parts. Sv from parts buffer. Buffer size. There we go. So, and let's actually start splitting this entire thing by lines, right? While content count is greater than 0, right? We're going to be doing string view line sv chop by delimiter, and the delimiter is going to be new line, of course, right? So this is the content, and this is the new line. So for now, I'm going to just count the lines just to confirm that this works, right? So st count. And then be initially 0, and then we can print something like this. Print f lines count zu count. There we go. So let's try to build this entire thing, right? And let's see how many lines we have. So we have 9,965 lines, right? We can try to confirm that that's the case. Teapot OBJ, was it 65? I already forgot. Yeah, it's 65. So we actually counted it correctly. So it matches with this thing. Okay, so that means we managed to split it by lines. As far as I know, we have one empty line. Yeah, there we go. So there's one empty line. So we need to learn how to filter them out. So I want to actually do something like sv left. I think it's like trim left. So we're gonna trim it to the left, and if line count is greater, count I said is greater than 0, only then we're gonna increment it by 1. So we're gonna have less than 1. Right, less by 1. Yeah, so now it's 64. So we filtered out one empty thingy in here. Cool. So, and the next thing we need to do, we need to basically identify what kind of entry within the file we're dealing with, right? So what kind of entry, because we have two kinds of entries, the v entry and the f entry. So I suppose v is a vertex, right? So it's vertex. So an f, I suppose, is a face, right? But it has like a 3 integers, so I presume this is a triangle, and indices are the indices within the array of vertices. So yeah, so it's basically indexed array. And essentially we need to read both of these things into 2 arrays, and we need to render the triangles by referring to the vertices in the original array. Right, so first thing we need to identify what kind of entry we're dealing with, whether it's a vertex entry or it's a face entry, right? So let's actually go ahead and sv chop by delimiter the line, the line itself, and we're going to chop it by the space, right? We're going to chop it by the space, and this is going to be the kind, the entry kind. Right, and we can have several of them, right? So far we have a kind v, which is the vertex, right? So this is the first one. The second kind of entry is face, right? Which is going to be f. Otherwise, we're going to say that we encountered a known entry. We can actually report an error like that, I think. I think we can report an error like that, right? So it's going to be something like a file path, and then we need to keep track of the current line, and we can say something like a known kind of entry, and we can specify svfmt, something like that. something like that. So this is going to be obj file path. Then we need to keep track of the current line for size t line number. So this is going to be something like this. So this is the line number, then plus plus line number. There we go. And we're going to specify that line number in here. And then we specify the kind that we just managed to parse, and in here then we just return the third one, which will automatically deallocate everything and stuff like that. So let's actually count how many vertices we have, right? So we can do vertex count and then face count, right? So vertex count is +1 when we encounter vertex, and face count +1 when we encounter that. So vertices is the vertex count, and faces count. So let's actually see how many of them we got. All right, so this one is supposed to be SV, literal. Sure. And what else do we have in here? So I don't have to increment anything in here. So faces count undeclared, so it's called face count for some reason, not faces. But I think it should be called... Okay, so let's call it faces for the consistency with vertex. Right, for the consistency with vertex, let's actually call it faces. Okay, there we go. So we've got 3,644 vertices and 6,302. That's a lot of fucking vertices for a goddamn teapot. The fuck, don't you guys think? Is there like a low poly thing? Teapot low poly OBJ file. I just realized that, like, holy shit. Low poly Teapot OBJ turbo squid. What the hell is that? No. Okay, Teapot Utah Teapot OBJ low poly file download. No, Utah download free and okay, so there is a Utah Teapot in here. Object detail to come. Alright, so we've got something. That's also a lot of them. Okay, let's go to the end of the file. It's just 1,000 of them. You know what? Why not? We are not rendering that in real time anyway, right? So that means we should be able to like render at least one frame. I'm gonna leave it as it is, whatever. So let me see. Okay, go. We need to introduce some data structures to store vertices and also faces, right? So I think it's going to be rather interesting, right? So this is going to be something like that, and so vector 2, or actually vector 3, right? So we're going to have vector 3. So float x, y, z, right? So this is the vector, and maybe vertex. Maybe we should call it vertex. Vertex, and then we're gonna have face, and the face is gonna be A, B, and C. So literally the indices of the face, or maybe it's a triangle. Well, let's call it face. Okay, so now we need to organize the dynamic array. Do I even have a dynamic array implementation somewhere? Can I steal it from somewhere? But yeah, so essentially, I like to implement. I think I already put it on the Discord. Let me search, because I do remember that I actually put my dynamic array implementation on the Discord. I wish Discord was a little bit faster and was handling the resize operation faster. It's playing animation, that means it gives the priority to playing animation, but not to resizing. Di append. Alright. Okay, so here it is, I think. So let me see. So we were talking about that. So I implement dynamic arrays with this macro. Right. It's a simple macro that accepts a structure that contains 3 fields, right? That contains 3 fields. For example, I want to have a dynamic array of vertices. So because of that, I'm going to define vertices. And here I'm going to have 3 things. The items, right? So this is the items. Then the capacity and the count, right? So in the way I can now work with this entire thing, I only need to define vertices, like so, and I can 0 initialize them as well. And if I need to push a new vertex in there, I do da append vertices, and then just a vertex, and just like values like x, y, z. There you go. But I need to parse x, y, z first, and it will actually like stretch and allocate and stuff like that. So maybe I also need to have something like make vertex x, y, and z. And as far as I know, it only evaluates that value once, so we don't have to worry about that yet. So it only evaluates it once. And on top of that, we'll have to parse and extract those floats from the line in there, right? So, and in here we have like a way to customize allocators and stuff like that. So initial allocation is around, we can actually like use something like, we know how many of those we have, right? 2 to the power of like 10, 14, maybe 13. So let's actually pre-allocate all of the arrays with this amount of elements, because it's like 6,000s and like 3,000s, right? So it doesn't like reallocate and stuff like that. And here, when we are reallocating, we're going to be reallocating within the arena, right? So we're going to do arena realloc. And I don't remember if arena realloc actually expects all of these 3 elements in here. All right. So yeah, there we go. So this macro is actually extremely simple, right? So if the count is greater or equal than capacity, right? If we exceeded all of the elements, we just allocate more memory. We just realloc. So and what's cool here is that we are referring to the items within the structure directly, so we don't lose any sort of like a type information and whatnot, right? So especially when we like refer to these items in here. Right, so the compiler can do whatever optimizations it wants. Okay, so a similar thing we can do for the faces, right? So this is going to be type def struct faces, and faces is a face, items. So it's like having templates, but in C, right? It's kind of like that. Okay, so this is the vertices, and then we're gonna have some faces. So faces, and we don't have to really count the faces anymore because we're literally creating them. So here are the indices of the faces, and then we are appending append faces, and what we're appending there, we make face A, B, and C. There we go. So, and then here we can do vertices count and then faces count if we want to. So we know very specific things in here. Okay, can we build this entire thing? Let's see. Doesn't build. Why? Because we don't have the make vertex and make face. So let's actually implement the constructors for these things. Vertex, make vertex, float x, float y, float z. So vertex v, maybe might as well just do something like x, y, z, return v. So what else do we have in here? So the same goes for the faces. We need to create the same constructor for this thing. So let's go face, make face, int a, int b, int c. All right. Face f, a, b, c, c. There we go. All right, so it didn't work because why? These things are incompatible. Why are you telling me that these things are incompatible? They are integers, this is integer, and we're doing integers, so maybe in the face itself, faces. Where is the faces implementation? Okay, so what exactly is not compatible? Assigning face that is not compatible. Okay, this thing returns face. ABC is a face. Faces itself is faces. Faces itself items are face. Not make face. Don't understand. Implicit declaration. Oh shit, okay. And Emacs using case insensitive search, and it's not helping. Okay. Alright, so, okay, so, we managed to actually put all of that stuff, so it actually worked, but it doesn't really put the actual data in there because they are zeroed out, right, so they are zeroed out. So we'll have to do something about that. So if we want to parse the floats, I think it's like str to, like, f, str to f, yeah, that's what we want, bruh. Wog. I'm sorry, okay. Alrighty. What is cool is that str to f. I don't remember if it like handles the spaces and whatnot, but maybe it doesn't really matter. It might not particularly matter. Okay, so here we have to provide the original pointer, and the original pointer is the line data, but we have to first trim that stuff. So we're gonna do line sv chop not trim left, right? We're trimming this entire thing, and then we provide this entire stuff. So we also have to provide the end pointer to know where it is going to end, right? So let's provide something like end ptr, right? And there you go. So, and this is where we're gonna store the x, right? This is where we store the x. And afterwards, we have to probably set the data to the end. Right, we need to set the data to the end. And I don't quite remember, if we couldn't parse this entire thing, I suppose it will just... The end is going to be equal to something, I suppose. If we couldn't parse it, but does it really matter? Doesn't really matter. Alright, so what we can do in here, I think, we can just continue piling those things on top, right? We're just piling those things on top, and let's see if we manage to work with all of that. Cool. What I'm thinking is that I want to go to GDB. I want to go to GDB and just look in the debugger if the vertices make sense. You know what I mean? Right, just want to see if they actually make sense. So maybe I'm going to use the GF debugger. Have you guys heard about GF debugger? It's not really debugger, it's a front end for GDB. Right, GDB GF. So yeah, I think I also need to like update it and fetch the latest thing. So yeah, it's actually pretty cool. I really like this thing. So it almost feels like Emacs, not Emacs, Linux has a proper debugger. Almost. Right. Okay. So let's actually go ahead and do the following thing. So I'm going to do soft. I think I already have it. Yeah, okay, I have it already installed and built. So let's just go ahead and just do that. So where are the files? The file is... I can't see shit in this mist. Okay, here it is. And let's go here. And essentially, I want to go somewhere here. Okay, let's run this entire thing. And we are in the debugger. So I want to take a look at the vertices. So in the vertices, we have 8,000 vertices. Do they make any sense? Okay, so they're not particularly readable because we need to take the data. And I wish I could just like take first like 100 of them, or this is not how it works. Vertices, data at 100. Why it doesn't recognize as an array? I don't remember how to make it as an array. Does anybody remember? Vertices data? Alright, so I dereference it and then I say give me 100, first 100. But I don't remember. I remember that in GDB it kind of worked, but here it doesn't work. Okay, I'm gonna try to do that in GDB. And if it works in GDB, I'm gonna be mad because I promoted this thing and it didn't work properly for me. So it's gonna be not gonna be very good look for this thing, unfortunately. Okay, so we're gonna break at try C, and the line that we have in here is 169. Okay, so let's actually run this entire thing. Okay, so we have vertices, right? And when I print the vertices, what do I say? Data, I dereference this entire data and I say give me first 10. No, 10. Oh, it's okay, it's just me being an idiot. I see. Yeah. It's items, not data. Okay. Okay, to redeem the tool, let's try to do that one more time. Sure. It's just me being an idiot. I'm already tired, as you can see. So, all right. Let's go here. Let's go. Okay, vertices. It's just because in string view it's called data items. I would say that we're going to have like 100 of them. There we go. Look at that. Boy, these are the things, and it can't display them. It literally can't display them. But I mean, I already kind of see that it makes sense. So it's like -3, 1.7999, blah blah blah. And if we take a look at the OBJ, it's -3, and it's kind of like very close to what I expect. So thank you so much, Drake Sorn, for 14 months of Twitch Prime subscription. If I missed anyone, I'm sorry. Mr. Karagos, thank you so much. Audacious Fish, thank you. All right, okay. So let me see. Now we need to do the vertices, right? So we need to do the vertices. It's probably one of the things I wanted to do is figure out the boundaries of the vertices, like X, Y. Yeah, X, Y, and Z, right? Because I usually expect a certain boundaries. And for the indices, it would be really nice to know their boundaries as well. But we'll go into that a little bit later. Okay, so we have float max X. Let's call them low X and high X, or maybe even LX and HX, right? So the low one should be maximum, like a float max, and high X should be minimum, maybe float min. I don't remember if that's the actual names of these constants, but I mean the compiler will tell me if I did something wrong. Doesn't really matter. Okay, if low X is greater than X, low X becomes X. If high X is less than X, high X becomes X, right? So this is basically what we have, and we're gonna repeat that for all of them. Could replace X with Y, boom, and another one is gonna be somewhere here. Replace Y's with Z. There we go. So that's what we have. Vertices, and we're gonna have something like this. So this is X, this is Y. This is Z. Low X, high X, low Y, high Y, low Z, high Z. There we go. So this is what we have. Let's see if we can actually see any interesting information. Okay, C limits float max. I don't remember the name. It's maybe it's something like FLT. Is it FLT? I don't remember. Yeah. Use event declared. Okay. Numeric limits. Limits for floating point. limits for floating point. FLT max, BLT max. So they probably also located in the Stack Overflow is being useful as usual. My god. Okay, so float.h. They're gonna work. There we go. So these are the boundaries. Very interesting. These are really strange values, but I mean, sure. We can try to divide x and y by 3, right? Because I want to feed them within the like -1, -1, and z has to be from 1 to 2. Yeah, we can try to do that. So specifically, I could probably even just like remap them, literally remap them at some point. Okay, so now let's collect the faces. So in terms of collecting the faces, do we have something like str to I? And I think that should be, it's not. So I think the standard way is like A to I, right? Oh, there was A to F. Maybe I could use that, but I mean I already use a different thing. Convert string to a double. Huh, is that a standard thing? I'm not particularly sure. It's supposed, yeah, it's actually a thing. And at the same time, str to I is not particularly a standard thing, right? Yeah, it's a netBSD extension. That's funny. But I can't really easily use this thing because it requires no terminated string, right? So that's kind of the problem. And I wonder, is there str to L? Yeah, that's what I want. Yeah, that's what I need. Okay. That's what I needed. Where is this stuff? Okay. So I can literally copy paste some of this stuff, right? So this is going to be str to L, and the base is going to be 10, and then I can simply do int A, right? Then B, and then C, and then I can just like put them all in there. Okay. So endpoint. And use declaration, so let's grab the end pointer. It's declared somewhere up there. Right, it's declared somewhere up there. Okay, cool. So, and I also want to know the faces boundaries as well. So it's going to be low face and high face, right? So in terms of indices. So the low one is going to be int max, right? So this is going to be int max, but maybe int min, and I do remember that you had to have limits or something like that. Unused variable, yeah, that's precisely what I want. Okay, cool. If LH is greater than A, if it's greater than A becomes A. If is smaller than A, this becomes that. And we need to repeat that for all of them. So I just want to know the parameters of that stuff. Okay, there we go. And let me see. Index. HF. There we go. So it's from 1 to. This is sus. This is definitely sus, so it implies that indexing is from 1. Okay, so OBJ format, index from 1. Waveform OBJ file. Vertex indices. A valid vertex index matches the corresponding starting at 1. Dijkstra is literally spinning in his grave. My god. Anyway, whatever. I can work with that. So, yeah, now we just need to, I guess, render this entire shit, right? We just need to render this entire shit, though not necessarily, probably. First thing we probably want to do is to like map axis, and since we already have these ranges, we can just do that automatically, right? We can do that automatically. Okay, good. So I already have some projection mapping in one of my examples, right? So something like Generalized Triangle 3D tech, and what is it? SDL, there we go. So as you can see, we already have this thing. So we can steal projection from here, right? So that's what I'm planning to do. Demos, 3D tech, and there we go. So we have a vector 2 and vector 3. Oh, that's actually really cool. So maybe I can steal some of that information. Yeah. Right, so we have a two-dimensional vector, three-dimensional vector, function that maps three-dimensional vector to two-dimensional one, and the function that maps two-dimensional normalized coordinates to the screen coordinates, so we can display them on the screen at least. So that's going to be very, very useful. That's going to be very, very useful, and I'm going to literally yoink all of that. So, and since we already introduced like a 2D thing and 3D vector, maybe it makes sense for me to get rid of the vertex thing and replace it with vector 3. Right, so to not duplicate the stuff, I think that will make sense, because then I can quite easily just take the vertex and literally just map it there and don't think about that stuff too much. So yeah, there we go. Okay, what do we have? Make vertex 3. Is it not? Vector. Sorry, vector 3. Cool. Yeah, this is a vector 3. So I wonder how much time it takes to just load it up. It takes some time, look at that. Half of a second. It takes half of a second to load this entire stuff and parse it and everything. Quite interesting. Alright. It's a high polygon thing though, right? So it's thousands of polygons. Okay, good. So we're about to render that stuff. How are we going to be rendering all that? I suppose we need to start iterating the faces and just putting faces onto the screen, right? So let's go ahead and do that. So it's going to be I less faces count, right? There we go. So we have the faces. So let's take the face. Faces items I. So this is our face. It has indices A, B, and C. And they correspond to the vertices, vertices items I, so this is the vertex 1, vector 3, so it's going to be, let's say it's V1, Zulul, right, so the next one is going to be V2, B, V3, C, there we go. So here are the vertices of our triangle in 3D, so here they are in 3D. The next thing we can do, we can project them onto the screen, right? So usually we do that by calling project 3D to 2D, right? And in this example, we simultaneously project 2D coordinates to the screen coordinates so we can instantly display them, which is actually kind of a nice idea, I think. There we go. So we constructed this entire thing, then we projected it onto the screen, and the only thing that is left in here is just like literally render that triangle. You know what I mean? Just like render it. We can go ahead and simply create a triangle. So Olivet's tree. Okay, so this is a tree. Olivet's tree new, right? So let's take a look at olivets.c, not this one. So there's one annoying thing about this project, is that the name of the project is olivets.c, and the name of the file, the main file, is also olivets. Olivsi. I'm sorry, I'm simultaneously pronouncing it in Ukrainian and in English. So, and when I switch in Emacs, I don't really know like what file or directory I'm switching to, so it's kind of annoying. Okay, will I use staging poke as a texture? I don't know how to put texture on the Teapot, to be fair. So to put a texture, I need UV coordinates. Is there already UV coordinates for the Teapot? I don't know. But as far as I know, people just like literally compute them themselves, right? So, and like figuring out how to create UV coordinates from the mesh, for me, for a person who never done that before, I think it's like a separate stream. Like I will have to dedicate a separate stream just for that. So probably not going to do that. All right. So this is going to be this thing. Only that's. I used to program the Teapot in 2002. It's so cool. In 2002, I didn't know what the hell is a computer because I was born in a third world country in a poor family. You're quite lucky. So imagine where I would been if in 2002 I had a computer. Holy shit. That's so cool. Unfortunately, like I didn't have a computer. I didn't even know what a computer literally. So, oh yeah, anyway. So, let's continue. Soon we're probably not gonna have computers at all, so who cares? We're going back in time. We're going back in time. So maybe this is my last computer, who fucking knows? And yeah. So if you knew that this is your last computer, what would you do on that computer? Watch porn? Come on. Program a Teapot. Utah Teapot. It's way more important than porn. Anyway, so what the fuck am I talking? Alright. So I'm sorry. Okay. Exactly. Who needs porn when you have a Teapot? Utah Teapot. Utah Teapot. Look at that. Look at that sexy Teapot. My god. Anyway, so let's continue. So right now I'm not really trying to fit anything into the normalized coordinates, right? I'm just like taking the data I got from the file and I'm just like putting it on the screen, and it's gonna probably look like shit. So we should be prepared that it's going to look like shit. Okay, so we're gonna lower our expectations. We're not gonna see anything special in there. Okay, so oh yeah, I remember. I wanted to open the thing. Oh, let's try. I set new. Okay, so here we just specify the coordinates, the vertices of the triangle. Nothing particularly special. So it's going to be P1 and it's just X. P2y, P1y. Yeah, there we go. And there we go. So this is going to be 2. And this is going to be 3. Okay. All right. Oh, it's already executing this loop, by the way. So that's actually kind of interesting. All right. So this is the first loop. The second one is going to be for. Oh yeah, we need to figure out the boundaries. So it's going to be V1 and not V1, Y1 and Y2. And this is going to be the vertical boundaries. So we provide the try. So width is, height is this one. So this is that, and this is that. And if this entire thing works, we're starting to iterate. Y1, Y2 plus Y. There we go. Cool. So we figured out the scan lines of the triangle. So what about the horizontal boundaries? Horizontal boundaries. Aha. Horizontal boundaries. So width y, and this one is gonna be x1 and x2. There we go. Oh, x1 and x2. So we're starting to iterate x, x1, x less than equal x2 plus x, And so we just do all of that. Pixel, we take a pixel of the current screen, X and Y pixel, and we just set this thing to, let's set it to blue. Yeah, let's set it to blue. I want it to be blue. Okay, that should be it, at least. So essentially we iterate through all of the triangles and we just fill them with the flat color. That's what we do, right? We just fill them in with the flat color. We'll see how it will go. It's probably not going to really look particularly great, but hopefully it will produce some sort of a result. Okay, so width is just a regular width in here. And we're also going to have an estimate for how long it takes, which is kind of cool, right? So, and it's actually relatively fast for a software render. So it took 1.2 seconds. Okay, so 1.2 seconds, and if we take a look at the PNG that we've got, it's completely blue. So, and this is probably because the Utah Teapot is actually too close, right? Because the entire system that I copy-pasted from a different place, it expects normalized coordinates -1, 1, -1, 1. And in terms of Z, I think it's from 1 to 2 because it's easier to project things like that. But I want to double check that. So yeah, so it's kind of interesting. So as you can see here, we have we put an object at 1.5, and this is because it looks the best from 1 to 2. Okay, so let me take a look at this entire stuff. So as you can see, Z is from -2 to 2, right? What we can do essentially, we can remap this range from -1 to 2 to 1 to 2, right? So this is what we need to achieve. So this is the source, and our destination is going to be 1, 2, right? How can we achieve such destination? Well, to the original range, right? So let's actually take a point, and we have to maybe add 2, or maybe we can just add the lower Z, right? All right, so I think I need to make a small break. So let's make a small break, and after the break, we're gonna continue doing about this thing. All right, so this is gonna be 5 minutes. Okay, so here is the following logic. Here's the following logic. So let's take a look at that from a general point of view. We have some sort of a range, right? So this is a low Z, and then there is a high Z, and we have Z somewhere here. So we need to first normalize it in the sense that low Z must be equal to 0. So what we can do, we can just do Z minus LZ, and it will bring it to something like this. So this is 3, and then 1, 2, 3, 4. HZ minus LZ, right? So, and then to normalize it to the value from 0 to 1, we have to divide it by the size between LZ and HZ, right? So, and to do that, we just do HZ minus LZ, right? So, and that give us a value from 0 to 1, which we need to then map to 1 to 2, right? To 1 to 2, which is rather easy because you just add 1. And yeah, I guess that's the easiest thing to do in here. Okay, good. So maybe, you know what, we're gonna have some sort of function which is gonna be called remap Teapot, right? So remap Teapot. And what we're gonna accept actually, so I suppose we should accept all of these values like LX, HX, LY, HZ. And by the way, I forgot a very important thing, chat. I forgot an extremely important thing. Why nobody told me? We have to do -1. We have to do -1 because this format was developed by Lua creators. Okay, so here we're gonna have low X, and set low X and high X, and then low Y, high Y, high Y, low Z, high Z. Okay, remap Teapot. So we're just remapping this thing. Remap Teapot. And there you go. So we just need to implement this specific function. Let's see how it goes. So this is a vector 3, and here we have another vector 3, v. All that is float, 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 float. There we go. Okay, so vz minus lz divided by hz minus lz plus 1. And we reassign that back to vz, and we return the new v. So in here, if we're going to add more remapping on x or y, we're going to put that into this function, right? So it's a centralized place where we do all of the remapping, right? Hopefully. Okay, so yeah, we effectively squashed it somehow and also remapped it to 1, 2. So we may start seeing something. Okay, so it complains about some of that stuff, so maybe I can just say lx. Let's say it's unused, right? Lx, hx, and I just don't want to see those warnings, right? So because it's kind of important for me to be confident in what's going on in the compilation process. Okay, so it takes half of a second to actually render and do everything. Okay, so again, it still probably looks like shit. So don't get our hopes, let's not get our hopes too high. But now, at least from the point of view of Z, it should be visible to some extent. That is rather interesting. So I feel like this is a bottom of the Utah Teapot. And it's rather smooth for like a triangle thing, so it's probably a bottom. So okay, so in terms of we can kind of do a similar thing for the rest of these things. All right, so we know their ranges, so we can also remap them somewhere. We might as well. So if I have a value from 0 to 1 and I want to remap it to -1 to 1, I will probably multiply it by 2 and get it from 0 to 2 and subtract 1, and it will get it from -1 to 1. So Vx minus Lx divided by high x minus low x, right? So this is the value. Then I multiply this thing by 2 and subtract 1, and this is the new x, and I should do the same thing for y. Boom. So, and most importantly, I used all of these things. So this is basically remapping that we do. Okay, so what do we have? Still half of a second, so it's relatively fast. Holy fucking shit! That's so fucking cool. Utah freaking Teapot. That is so fucking epic. Yes, we did it. Let's actually shade that mother flipper. I think we have some time to shade that mother flipper. So the world record. Yeah, so I saw some YouTuber, like a game developer, I think, came up with a meme that basically speed run the rainbow triangle with OpenGL, which I also want to do at some point. Right. So, but here we basically speed run Utah Teapot without OpenGL. How about that? Right. So that's actually super cool. Cool. So let me see if, like, how can we shade everything, because we already have like a very simple shading in one of the examples. Right, so demo texture triangle 3D texture SDL. So this is the example that we have, and you can see there is a little bit of shading in here, and it's achieved through looking at the Z values. Let me double check how exactly we do that, because I don't quite remember. All right, so in here, so we blend the colors and we take a look at the Z value. Right, so if z is less, we put one thing, then we put another one. So z1 becomes inverted. Oh, so we look at the original one, and if it's greater than 1, we bring it back. Yeah, we literally use z as the alpha of some sort. Not even alpha, we're like literally, yeah, we use it as an alpha. Let's give it a try. So we'll probably have to put some sort of like a z buffer in here. And we'll also require interpolation and whatnot, but I think it should be fine. So here are the pixels. Let's introduce the z buffer. There we go. So we have a z buffer. Interestingly enough, if the z buffer, yeah, that's fine. That's fine. So since we're not do any z testing, the lighting might actually look pretty weird, but then we can actually add that thing and it should be fine. All right. So essentially, I need to do the barycentric coordinates, right? So it's going to be u1, u2, and the determinant. So barycentric coordinates is basically the coordinates on the triangle, which tell you how close or far away that specific point from all the 3 corners, right? So, and you can do interpolation of the values, right? If the 3 vertices have different values, you can smoothly interpolate between these 3 values using these coordinates. So that's basically what it's all about. So, and we need that because we need to interpolate the z value. So we can know the z value of specific pixel that we're rendering. So that's basically what we're doing. All that, and let's do barycentric coordinates. There we go. So this is the triangle, so this is the point, and we return the barycentric coordinates in here. There we go. So, what we want to do? We want to take the z values of all 3 vertices, right? So, and the z values are going to be like this. So p1 z, then p2z and p3z. And now, knowing the z values of the vertices, we need to find the z value of that specific pixel we're currently working with. But since we're dealing with projection, we cannot linearly interpolate between z values because on the screen they're non-linear. But what's linear on the screen is their inverted values, right? Their inverted values. So they are in fact linear, and we can try to interpolate between them. So then I'm gonna multiply this entire thing by u1. Yeah, so I can do u1 and divided by the determinant, then multiply by u2 divided by the determinant, multiply by determinant minus u1 minus u2, divided by the determinant. So, and then I can sum up these 3 values, and I get the z actual, inverted z value of that specific thing, which I can then put into the z buffer, right? So this is going to be z buffer. Right. Z buffer. So it's going to be y multiplied by width plus x. But it would be also nice to do a little bit of the z testing actually, right? Essentially, if z is less than whatever we have in here, it will be put in there, right? Otherwise it won't. And when it's put in there, we also use that z value like so. Okay, so we put the z value and we assign it to z. And we also should use that 3D texture. Yeah, like so. So v becomes that, so we use z as a parameter in here. But first we'll have to do something like -1, I suppose. So this is going to be -1. Because it's from 1 to 2, we have to do that. So then Yeah, and then so then we blend the colors. I see. So that means I can assign this thing, and then I can additionally blend this entire thing in here. Right. Okay, so interestingly, since this is inverted, right? We have to keep in mind that this is inverted. That means that we're only looking for those that are bigger, right? So if it's bigger than whatever we have in here, that means we're going to replace it anyway. So then we're going to put this thing in here, right? Then save it, and then we should not forget to do something like z divided by z 1 over z. So, okay, I need to double check because it's really easy to confuse yourself with this logic, right? So we have the current z value, and we have, the current value in the z buffer, right? And the value, the new z value that we've got. So we only care about those that are bigger. If you find the bigger one, that means that the one you have to put. If it's smaller, we keep the original one. So if we found bigger, we just put that thing in the z buffer, right? We just put it in the z buffer and also put that thing into the color buffer. Next thing we try to do, so this is just the z testing. And the next thing is going to be shading, right? In a shading, we invert the z back, right? We invert the z back. So here I also for some reason check if that z is greater or equal than 1. I'm not sure if it's needed in this particular case, but I'm gonna do that anyway. Right. Then I also reduce it by 1 to bring it to a range 0, 1, and then I just use it as a shading, right? So if for whatever reason we exceeded 255, we're gonna keep it to 255, and only then we're gonna shade it effectively. Right, it's not perfect solution, but it's fine. Okay, since we're only setting those that are bigger, right, we're only setting those that are bigger, we should probably fill the entire z buffer with zeros, right? We should fill it with zeros. And let me take a look at the z buffer. Where do we have it? So let me fill it with zeros. So this is 0, this is 0. That should hopefully work. All right. And the reason why we're checking that it's greater than 0 is probably because we not want it to be equal to 1. I think we really don't want it to be equal to 1, right? Because it's, if it's equal to 1, you may have like a division by maybe not. No, whatever. Okay, so let me see if this entire thing compiles. Maybe it will compile, maybe it will not. Okay, so we have this kind of stuff. Z is not a member. Oh yeah, so because we have to take the original vertices, not P1, but actually V1, V3. Right, so let's give it a try. Another one. This is not OC1, this is original OC. Okay, it's still that, and if we take a look at this stuff, this mother flipper is shaded. This mother flipper is shaded, yo! Properly, by the way. Look at that, look at that. Holy shit. Well, I mean, almost. I mean, so you can see kind of edges between the yeah, between the polygons and stuff like that, but it's shaded, all right? So it's kind of shaded, so that's really freaking cool. So let me, what if I just make it like white completely? Yeah, this is without OpenGL. We literally render it pixel by pixel ourselves, without any OpenGL. So we can make it like whitish, so it's like pops. All right, so let me see. What if we just do something like 120? So let's actually do it as a factor. So I want to do full HD rendering. Let's do like a high resolution full HD. You know, because we're in 2022, we can afford that with our modern powerful computers to render shit in full HD. Okay. So as far as I know, Full HD is like 120, right? So around this time. So let's see how much time it will take. And it's taking some time. We're rendering a single frame, so without OpenGL, one frame takes 2 seconds. Yeah, that's pretty cool. So interestingly, oh wait a second. Do you see any optimizations in this command line? Okay, let's take a look at the Full HD. This is Full HD. So of course we don't take into account aspect ratio, right? So that's why depending on the resolution you're gonna have like different things. But overall, right? So yeah, that's what we have. And this is on without any optimization, right? What if I enable at least O2? At least O2. O2. How about O2? A little bit of O2. Half of a second. O2. What about O3? It's not that much, but I mean, yeah. So, and I'm not even using CMD or anything like that, so yeah, it's pretty cool. Let's take a look, and here it is. That's the result of today's stream. 0.5 FPS, yeah. 0.5 FPS. Man, that is so cool. And this is high poly, by the way. So we can also make it rainbowish. Who said we can't do that, right? So because since we're interpolating, right, we can just mix the colors, mix different colors. Let me try to do the following thing. So we have something like mix color 3, but okay, order that. Mix colors 3. So these are the parameters that we're trying to mix in here. Okay, you in 32. There we go. So, and what are going to be the colors that we're going to be doing in here? 0x, FF. So this is going to be red. This is going to be green, and this is going to be blue. I know that they're in a different order, but this is because of the, you know, little engine and whatnot. So U1, U2, determinant minus U1 minus U2, and the determinant itself. So that should actually, each polygon should be rainbowish, if you know what I mean. Each polygon should be rainbowish. Right, and let's see, it's, okay, so it's compiling. And it's still rather fast, even with all of that shit. Yeah, there we go. Man, this is so fucking cool. Holy shit. Yeah, you can see the actual polygons. Let's actually add transparency a little bit. Can we add transparency? I think we should be able to add transparency. Though, in terms of transparency, nah, it's too much. So I'll need to figure out in which, how to properly, when to just copy it and when to do transparency and whatnot. And it would be also kind of cool to maybe simplify this model a bit, right? To the point when we can render it at least some reasonable amount of FPS, maybe like find a low polygon version. Right, so if you can find like a version with less amount of polygons, we can turn this into animation, right? We can turn this into animation as we do in demos and stuff like that. So yeah, so there's a little bit of weirdness in here. Yeah, there's a little bit of weirdness on the edges, so I'll probably have to investigate. But overall, maybe it's something with a Z. Who knows? Who knows? There's some artifacts. Man. No, we're all kind of cool. Alright, so does anyone have any questions? Any questions? Because I'm already streaming more than I supposed to stream, so just not real time. You do multi-threading or AVX? I do plan to actually explore how to improve the performance with AVX and multi-threading, that's for sure. Can you simplify this model with Blender? Probably, but I don't know Blender, so we have to spend some time just exploring. If somebody can simplify this model and just like give me an OBJ file with a simplified model, that'd be kind of cool. Are you planning to write it on GPU? No? Why? Did the instance correctly? Yes, I checked that and fixed that. So, yeah. I double check that. We can double check that one more time if you want. Sure. Oh yeah, here it is. So vertices items, and here's the indices f.a-1, f.b-1, f.c-1. What about coding decimate algorithm? I don't know what's the decimate algorithm. Decimate algorithm. What is that? I've never heard of it. Done. Decimation. So basically lowering the amount of polygons, right? That's what you mean. Yeah, you can think about that. Maybe. I don't know. It's too outside of the scope of what I'm doing. I mean, whatever I did right now is already quite outside of the scope of what I wanted to do with this library. This library is supposed to be like a simple thing that allows you to quickly prototype things that draw rectangles and lines in case you want to just quickly check something. It's not supposed to do that. I kind of, yeah. I got a little bit carried away, that's what I would say. So originally I planned like a simple thing that allows you to draw simple primitives. And now we're rendering high polygon Utah Teapot with Z-testing and shading. So yeah. Could you tap the API for it to support making animation without using other software? I can't, because I at least need to interact with the operating system, and the operating system is already kind of using a different software. Alright, so can you try more complex objects? Wait a second. Is 3,644 vertices and 6,320 faces not complex enough for you? It's not. You guys are spoiled. You guys are straight up spoiled. This is not complex enough. This is not smooth enough for my gamer taste, for my exquisite gamer taste. My God, so spoiled. I just can't. I just can't. All right. So, okay. So maybe we should rate somebody. What do you guys think? Stand for dragon? Is there something? Okay, wait a second. I can stand for the dragon OBJ file download. I don't know what it is, but it sounds like it's something. Okay, stand for a 3D model for free. Okay, let's download this big. Can I download it? It's thinking. My computer is too slow for that shit, I'm sorry. Alright, so I wanted to rate somebody, I kind of changed my mind. Alright, so that's it for today. Thanks everyone who's watching me right now, really appreciate it. I'm gonna, you know, commit and upload it after the stream, so you can play with this example if you want to. Have a good one, and I see you all next time. So for the next time, I'm gonna try to come up with also something interesting. So today's stream was actually rather cool. I really liked it. All right, so that's it for today. Love you all. Mwah.